Hi, it's time for another math easy solution, and today we're going to discuss another applied project. Basically, applied projects are just some pretty interesting math projects at the end of each chapter in my calculus book, and I've done some others before, so make sure to watch those in the video link below. And this time I'll go over this one, which is how fast does a tank drain? And we'll go over question 1 of this. There's multiple questions. I'll just go over question 1 in this video. Basically, let's just go through this this project. So if water or other liquid drains from a tank, we would expect that the flow would be greatest at first when the water depth is greatest, and will gradually decrease as the water level decreases. And you can just picture this with a bathtub or whatnot. When it's really filled, just because of all the weight of the water, it will push that water faster down when you have the water depth is really high. Then as it gets lower and lower, you would just assume it would gradually decrease, because again, it's the weight of the water pushing down on that small hole. Okay, but yes, but we need a more precise mathematical description of how the flow decreases if we want to answer more complex questions, like basically the ones that engineers ask. For example, how long does it take for a tank to drain completely, and how much water should a tank hold in order to guarantee a certain minimum water pressure for a sprinkler system? And I'll go over those as we go through this applied project. So let's first define h of t and v of t to be the height and volume of water in a tank at time t. So if water leaks through a hole with an area A at the bottom of the tank, then Torricelli's law, and I'll hopefully in later videos I'll go over Torricelli's law derivation in more detail, but for now we'll just write that down. Basically says, well, I'll write that in a bit. Let's just draw this out. So let's say we had a tank, a cylindrical tank, could be any shape, doesn't matter. So yeah, it's something like this. So basically what we're saying is the volume of water and the height of the water. Let's say you have a tank like that, and inside you have this water. So I'll just draw a little buoy or whatever. So that's our water, and this is a height h of t, that's the depth, and inside has a total volume v of t of that water. And then this area here, let's just say there's a hole across here where it's leaking through, and this has an area equals A. Then Torricelli's law states that the rate change of the volume of water in this tank, dv over dt, is equal to negative times A, the area of that hole, times it by the square root of 2 times gravity, or g, and then times by h, the height of that water. Yeah, and again, where g is the acceleration due to gravity, just write that down there. And so the rate at which water flows from the tank is proportional to the square root of the water height. So that's what this Torricelli's law states. So again, the flow rate of the water is that's leaving is proportional to the square root of the height. So let's go over question 1. So question 1 of this applied project states, suppose the tank, well, it has 3 parts, A, B, and C, and the part A says, suppose the tank is cylindrical with height 6 feet and radius 2 feet, and the hole is circular with radius 1 inch. Let's just draw this out first. So we have a cylindrical tank like this, and it is 6 foot tall. H equals 6 feet, and as a radius, we'll call this R. R is equal to, what is that? 2 feet. So working in feet right here, and at the bottom it says there is a hole, is circular with radius 1 inch. So that's this one right here. We'll draw that like that, and basically this has a radius of, I'll draw a better line like that. So this has a radius, we'll call this R of the H, R of the hole, R, H, actually not A. So our h, radius of the hole, is 1 inch, which equals to, well, again, 1 inch is just 1/12 feet. Let's just write everything in feet right here because we have feet over there. And then part A, again, it says if we take G as the gravity, and this is in imperial or American or British units, 32 feet per second squared. So we have G is equal to 32 feet per second squared. I'm just writing everything we know right here. And then now it says, show that y satisfies the differential equation dH over dt. Yeah, actually, before I get to that, I just realized this is just a typo that my calculus book has. This is a typo. I don't know why it says y. Show that y satisfies the differential equation. I don't know what they mean by this y exactly in my calculus book. But I'll just write this down in case you have this exact same calculus book or the same project. So I'm not sure what this y means. Basically, what we're just trying to say is show that this type of cylindrical tank with this kind of radius and hole radius satisfies this, and with this gravity as well, satisfies this differential equation. So that's what we want to find out. And then part B says solve this equation to find the height of the water at time t, assuming the tank is full at time t equals 0, and C is how long will it take for the water to drain completely. We'll get to those in a bit. So basically we want to satisfy this equation, which is, so we want to show that dH over dt is equal to -1/72 times it by square root of h. So we want to show that this is the case. And now we could do this by, well, first thing we have to notice is that this is the rate change of the height, and this right side looks pretty much like our Torricelli's law right here, but this is volume. But we know that the formula of volume, you could write it as a formula of height. That's just the area of this circle times it by the height, which if we recall, that's right, recall the volume of a cylinder is simply, this is just the area at the bottom or the top, pi r squared, times it by the height of the cylinder. So that is the volume, and in terms of h and r. But this one here, we want to, basically what we're trying to get at is write Torricelli's law as a rate change of height and not volume. So you could just take the derivative here. So we take the derivative dv over dh, actually not h, we're going to take the derivative in terms of time, I mean. So when we take the flow rate dv over dt of this one here, and again, radius here is constant because its radius is always there. Whenever the water, wherever you have the water, let's say you have it like this. So let's say you have the water like that. This water always has the same radius. The height changes. So let's write h of t like this. So the height changes, the volume changes as well, but the radius is always constant. So the derivative in terms of time, this is going to be equal to, well, this is just all constants, so pi r squared, and h is a function of time, so we would have to take the derivative of dh over dt. And then the radius is constant, so let's just solve this out. So this is pi, and then r is 2 feet. So 2 squared times dH over dt, and finally this equals to 4 pi. So 2 squared is 4, so 4 pi dH over dt. So now that we have this, well, we just apply the Torricelli's law, which is dV over dt equals to -a times square root 2gh. So this also equals to dV over dt is equal to -a times it by 2gh, where the area A right here, so this is the radius RH, the area is basically just a circle, so pi r squared, or pi r h squared, so this equals to -pi r h squared times it by 2 times g, where g is 32 feet per second, and then times it by h. Again, h is just a function of t, so 32 times h of t. And I'll just put h right here. So I'll just write h for this one right here, h max for the highest, or the tank, or h of t for the tank, and then this t, just differentiate this as the water height, and this is just a full tank height. So we have this, that's why we put this h, so it's not 6, it could be anything. And now we have this, let's solve this out. So this is negative pi, just simplified, r, yeah, RH, remember RH was 1 inch, and 1 inch is just, well, 1 over 12 feet. In other words, 12 inches is 1 foot. So we'll put this as 1 over 12, because we're getting all the units, just make them all aligned with feet, etc. So 1 over 12 squared, times it by, this is 2 times 32, that's just 64. And what I'll do is I'll square root 64 and get this out, square root h. So you could just do that, just to get this square root h by itself. Now what we have is negative pi over, no, negative pi times, in square root 64, that's just 8. 8 times 8 is 64. Times it by square root h, and then at the bottom we have 12 squared, which is, well, 144. If you could just do that in your head or calculate out. So we have this. Let's simplify this even further. And to simplify this further, we have, well, let's divide this out by 2, that's 4. 144 divided by 2, that's, well, 70 times 2 is 140, and then so 72. Now we could simplify this further, but what we're going to do is we're going to equate these two. So these are equal because we have this, and there's the 4 there, so there's a 4 here. We'll just leave that because it will cancel. So this ends up equaling to negative 4 pi, and then 72 times square root of h. Let's get rid of that. So times square root of h. So let's equate these two. So this is the flow rate from Torricelli's law, and this is just the derivative of the volume of a cylinder right here, and that's to get in terms of the flow, in terms of the rate change of the height. So what this means is, so according to this one here, this one is, so I'll put this one first. So this right here has to equal this right here, because those are both dv over dt and dv over dt, just found from different methods. So let's write the first one out. 4 pi dh over dt equals to now negative 4 pi over 72 times square root of h right there. And as you can see, the 4 pi's cancel. So what we'll end up with is what we were trying to solve. So dh over dt is equal to negative 1 over 72. Oh, that's too far to line. So times it by square root of h, and there is our answer. Let's just highlight this a bit better. So there it is. And this, in fact, is exactly what we were trying to show that it's there. So show that dh over dt is equal to negative 1 over 72 times square root h. That's here as well. And let's just put a check mark there for having it correct. So let's look at part B now. Part B says solve this equation to find the height of the water at time t, assuming the tank is full at t is equal to 0. In other words, what it's saying here is that the height, assuming it's full, so then the height at t equals to 0 equals to just simply h of 0, which equals to, it's the full tank height, which is 6 feet, and that's the full tank height because it's full. So cylindrical, the tank is 6 foot in height. So it's 6 feet, and we want to solve for this equation, and this is our initial value there. So we'll write part B. This is a differential equation and with an initial value. So we have an initial value problem, and I've gone over these in my earlier videos on differential equations, so make sure to watch those in the video link below. So initial value problem, where we have a differential equation dh over dt equals to negative 1 over 72 times square root of h, and we know that h of 0 is equal to 6 feet. So we have this, and this is a separable equation. So separable equation actually, because this square root of h, we could separate it so that all the h's are on one side and all the t's are on the other side. So this is a separable differential equation. I'll circle that. So that means let's just move this around. So move this over there and the square root of h on the other side. So what we end up getting is a 1 over square root of h times it by dh is equal to negative dt. I mean negative 1 over 72 times dt. So we have this, and then we just take the integral on both sides. So we take the integral on the right side right here. This is a simple one to do. This is just a constant, so integral of just a constant is just going to be that variable t right there. 1 over negative 1 over 72 times it by t. I'll just put that here actually. Put the t there. Then we have to plot a constant. We'll call this constant c2. I'll put the c1 constant on this side. That's just the integration constant. And now this one here, to solve this, let's just simplify this a bit further. It's the same thing as writing h to the power of negative 1 over 2 dh, and then the integral of this is equal to, this easy way to do it, I like putting the negative power like that. So we have to add 1 to it, add a power, so that's h 1/2, and then divide this by 1/2. So when you divide by 1/2, you get a 1 over 2 like that. So that is, I'll just erase that 1. So this is going to be, now we have to add a constant, called c1. And again, if you look at this, take the derivative, this 1/2 goes down, and then you minus a power, which will get negative 1/2, and the 2's cancel. Anyway, so that's what we have right here. So put these all together, what we end up getting is a 2h 1/2 plus c1 is equal to negative t over 72 plus c2. And now I'm going to simplify this even further, and now I'm going to put this as 2h, let's put the square root now. 2 times square root of h, and then equals to negative t over 72 plus c, where c is simply just the combination of the two constants, so c2 minus c1, and it's still an arbitrary constant. Just to make it simpler to look at and solve. So now we know the initial value. We could solve this further, simplify it further. We'll do that actually afterwards, and I will just do this first. So we know that h of 0 is equal to 6, so let's just plug that inside. So what we get is this 2 times 6 is equal to negative 0 over 72 plus c. So this is just 0, so what we get is c is equal to 2 times square root of 6. So we have our c value, and now we could just go ahead and further simplify this h formula. So we get 2 square root of h is equal to negative t over 72 plus c, which is 2 times square root of 6. So now let's divide everything by 2, and what we get is a square root of h is equal to negative, well, 72 times 2 is 144, because we're dividing it by 2, and then this 2's cancel, plus square root of 6. And then, well, what you could do is square both sides, so we can get rid of this square root sign. That's just the power of 1 over 2. Those add up, becomes 1. So what we end up getting is h is equal to negative t over 144 plus square root of 6. So there is our formula. Yeah, so this is our formula for the height with time. And now let's look at part C, the last part of the question 1 of this applied project, which says how long will it take for the water to drain completely? In other words, what we want is basically what is h of t, and what is t when we have the height of the water is 0, and t equals to what? So that's what we want to solve. So let's go all the way down and write this down. So part C, we want t equals to what if h of t is equal to 0. So when the height is 0. So let's just plug that in. So we have a 0 is equal to negative t over 144, write a better t, plus square root of 6, and then this is all squared. So square root both sides, like that, etc. This just to get rid of the 2 right there, and this is square root of 0, 0, so we still have 0 is equal to negative t over 144 plus square root of 6. So let's move this square root of 6 on the other side, or move this t divided by 144 on the other side, and multiply it by 144 and everything. So we get is t is equal to square root of 6 or 144 times square root of 6. So just rearrange, solve it for t, we get this. And this is actually in units of seconds. And the reason is because everything, we had the gravity as 32 feet per second, and that's where we get the seconds from. So our units were feet and seconds. And now if we were to type this into a calculator, just calculate out. So 144 times square root of 6 is 352.72, etc. I'll just round this up to 353 seconds. And again, we're not used to counting in seconds, like such large seconds. So how much this is in minutes? Well, this equals 2. You could write this as, well, just multiply this out actually by, let's go with 1 minute over 60 seconds. Because 60 seconds is in 1 minute, so we multiply this out so we can cancel this units. So what we end up getting is what we could do is 300, I'm going to separate this into 2. So 300 plus 53, because 53 is less than 60. So what we have is like this. So we have a 300 plus 53, and the units here is in minutes because we canceled the 60, the seconds right here, and this is simply equals to 300 over 60 plus 53 over 60. So then this one right here, 300 divided by 60, that's just 50. Or that's just 5, So this cancels, and then 30 divided by 6 is 5. So we get 5 minutes, and then plus 53 seconds over 60, over 60 seconds. This is, this is 53 seconds. If you divide this out, you get whatever the minutes were, but we'll just leave it at 53 seconds. So we'll get 5 minutes and 53 seconds. Or in other words, 300 seconds plus 53 seconds. But if you have the 60 right there, so I'll just write this is t is equal to 5 minutes and 53 seconds. Yeah, and this is just an easier way to understand just how long it takes to drain, as opposed to just saying 353 seconds. Converting this to minutes and seconds, it's 5 minutes and 53 seconds. This is something we're more familiar with. So the tank will drain after 5 minutes, almost 6 minutes. Anyways, that is all for today. Hopefully you'll learn from this pretty extensive question 1 of the applied project. I have some other questions we'll go over in later videos, so stay tuned for those. Hopefully learn from this pretty interesting applied project. And like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.